Yeah, you can sort of like line up against the wall. This tutorial is, you can do it on your laptop, or you can just sort of like listen and watch. It's up to you. So my name is Cameron Davidson-Pilon, and again, I do want to thank you for coming. This is very exciting to me. I love this topic. It's been my kind of like side hobby for the past 9 months, so I want to brain dump that all onto you. So I used to work at a e-commerce company, Shopify. That was for about 5.5 years. I ended back in last December. Since then, I've been doing food science and food science projects, applying data science to food, and that's been really interesting. I'd love to talk to you about that afterwards if you catch me. Before we kind of begin, I kind of want to play a little game just to sort of like loosen everyone up. Who here thinks they traveled the farthest to get to New York? We got 1 hand, 2 hands. Okay, we'll start like, go ahead, you on the floor.
London.
Oh, that's pretty good. Amsterdam, that is farther probably. Who knows if that's farther? Yeah. Probably farther, yeah, definitely, yeah, okay. I thought Ottawa was gonna win, or like that, I guess not. Okay, so Oslo, well done. You're gonna be disappointed by this. So the tutorial is broken up into 2 sections. The first section is going to be using our IPython notebooks or Jupyter notebooks. It's going to be kind of computer work, mostly focused on estimation and sort of the new trends in estimation I want to show off. The second half, though maybe the last third, is going to be about inference and how to interpret your estimates and sort of modern interpretations of inference. How the sort of deep thinkers in this field are thinking about science and statistics and inference. When Jane contacted me about doing this tutorial, it was originally supposed to be a statistical models tutorial, and I was like, yeah, that's interesting, but what I really want to talk about is estimation in general and inference, and so I pitched that to her, and she was excited, and I was just giddy. So yeah, I am very happy to be here talking about this. So one note, you can git clone from this repo if you want to follow on your computer. If you do follow, just be mindful of when you're distracted, everyone around you is going to be distracted as well if they're looking at your computer screen. So if you feel you're going to be distracted, kind of just like use your phone or just be mindful of the others around you who will also be distracted. And finally, please ask me questions throughout, and let's make this a discussion and kind of a QA thing. I might leave some time at the end for questions, but I kind of want questions in between because that's going to help me gauge where y'all are at, and it's a great way to sort of spur more motivation and spur more understanding of these topics. One more thing about Bayesian versus frequentist. So a lot of you might know me as a Bayesian, but that's just a hat I wear sometimes. I also put on a frequentist hat very often because both methods are really useful. If I were to sort of like prioritize things, I would say try a Bayesian approach at first. If that doesn't work, do a frequentist. But frequentist methods are still really useful, and they should be discussed, and they're really fun to do. So this talk is going to be more about the frequentist ideas, but you're going to notice like a lot of Bayesian flavor in the inference and the estimation approaches. Okay, great. So I'm going to assume you've done this. If not, just find me on GitHub, and you can find this repo, and then go ahead and git clone it. If you've already done that, do a git pull because I've maybe updated something since the last time you cloned it. But let's begin. So we'll start. If you go to the repo, we'll open up the Jupyter notebooks using your command line. If you're having problems, just like maybe ask the person next to you. You also would have to pip install the requirements file if you haven't done that already. Most of it's part of the normal stack that we're using. There might be one exception called autograd, which I'll get into later. But try doing that if you haven't done it already. Okay, so we're going to go to the tutorial notebooks, not the full notebooks. Those are for reference later. So tutorial notebooks, there's just some pieces missing that we're going to fill in as we go. And we're going to start in part 1. Let me just make sure. Great. And the people in the back, can you read that okay? That's good? Great. So we're going to fit some data to a parametric model. And a parametric model, it's sort of fully specified. It has unknown parameters that we want to fit the the data to. I mean, we're just curve fitting essentially using like something a bit more advanced than linear regression, but that's what a parametric model is. We want to create the log likelihood, and then we're going to optimize over that. So the log likelihood contains all the information, contains like the parametric model, contains the data, and we want to maximize that function. We'll create some fake data first. Remember, shift enter is how you kind of execute these cells. So shift enter, we can see this is our data. So that's a data generating process. Doesn't really matter how we got this data, but it looks like this. And we want to fit some parametric model to this. So the first, for positive data, and this is strictly positive data, a really good approach is the Weibull distribution. I'm not going to make you type this out because it's complicated and very error prone. But it looks like this. There's two parameters, lambda and rho. Lambda is like the scale. It kind of defines like the units of your data. And rho is this kind of flexible parameter that defines the shape. But this is the PDF in Python code. The log PDF is actually what we need for the log likelihood. And again, I'm not going to make you type this up because it's super error prone. The last step is this log likelihood. It just takes log PDF of the params and t, and we just sum it all up. That's the log likelihood. Cool? Any questions? You shouldn't have had to type anything yet, so this is easy. So we execute this. Great. And the first kind of like core function we're going to use today is SciPy optimize minimize. I use this all the time. It's really, really useful. It's great not even for both continuous and discrete problems, for parametric and semi-parametric problems. It's as easy as entering in log likelihood and some initial guess if you want. Method, we're going to touch method today. By default, minimize, we'll try to minimize the first argument of the function, which in our case is params, which we want to minimize, or we want to sort of like optimize over that. But you pass in sort of extra arguments in this args function. Okay, so this is where we start typing. Let's enter in some initial guesses for these parameters. So we have two parameters, the lambda and the rho. So we have to give it a two-parameter array, or two-length array. Rho and lambda are both strictly positive, so it makes no sense to put 0 and 0. That's not really going to do anything useful. So we're going to put 1 and 1. Those are pretty good defaults. And OK, yeah. OK, I think this is just going to work. Cool, we got nan. Is that expected? One moment. Yes, OK. So we got a nan. What happened? Well, there's a bunch of like warnings here and stuff. The problem is that this is minimizing something, but we want to maximize the log likelihood. So really what we should have done is put a negative sign in front of what we just did, or we had up there. So it should be like negative np.sum. This sounds silly, but like this is one of the most common mistakes that people make. Log PDF. That they forget that you want to minimize or maximize the log likelihood, so you want to minimize the negative log likelihood. And that should fix things if you try again. Oops, where am I? That did not work. Where did I? Oh, right. Sorry. Yeah, there's actually one more thing we have to do. OK, so this is the final piece to this minimize thing. Like I said, rho and lambda are strictly positive. So we need to tell minimize that they're strictly positive. That's the thing we're missing. Because minimize thinks it's the entire reals. So it's going to say, like, oh, let me try -1. And you're taking, if you go back to that log PDF, you're taking the log of -1. It makes no sense. So we're going to put in this final argument, bounds equals. And then how it works is it takes a list of bounds. So because we have a bound of 0 and a unbounded right-hand side, we just put like 0, none. And that's for both parameters, so 0, none. Just a bracket. Cool. And it still didn't work. We're getting there. This is literally what you have to do when you use minimize. Like, I've had to do this so many times. OK, one more thing. Technically, 0 doesn't work either, because what the algorithm is going to do now, the optimization algorithm, it's going to try 0, because it's a boundary condition to see, like, well, maybe the boundary is the minimum. It's going to fail because log of 0 is still nan. So we're going to put in these very small constants. Wonderful. Good. OK. So these are our unknown values that they're now known values that we've fitted. So these values maximize the likelihood, the log likelihood, which tells us these are like the best values for this parametric model. Oh yeah, and then so yeah. So the takeaway is minimize. It's very flexible. It can do like, you can put in bounds, you can put in args, you can change the optimization algorithm. You can kind of like, and this is actually very, very useful, you can give it good initial guesses, because it's actually quite, like most problems are not going to be convex and really lovely bowl-shaped problems. So the right initial values is going to give you a better solution. So minimize is very, very general, and it's like a workhorse that we can use often over and over again. It's good for small to mid-sized problems. As you get into like higher and higher dimensions, you might want to switch to, and in that case, it's harder to reason about the convexity of this bowl or this likelihood. So you might want to use like a gradient descent algorithm. And maybe in that case, you don't really care about finding the actual global minimum. So a gradient descent would work pretty well. For now, for our tutorial, we're going to stick with only small to mid-sized problems anyways. So we'll stick with this. Good question is like, what does mid mean? And I don't know. It could be 100. It could be 12. It kind of depends on how much data you have. Depends on your domain. It depends on like how complicated your model is. But we'll stick with that. OK, a few problems though. We're stuck using only parametric models that are relatively easy to implement. They have like a closed form solution. They're sort of like relatively easy to write down in code. And we're still using minimization routines that don't use any gradient information. So that likelihood, think of it as a bowl. Our optimization algorithm is just picking a point, kind of looking locally as to what's less than where I am, and going in that direction. It's more complicated than that, but it's not really using gradient information. It's just kind of hill climbing down. So we're going to do better. For that, let's move on to part 2. I have to go here. Part 2. So if you know me, I really like survival analysis, so we're going to do some survival analysis. I like it because it uses the main tool of today 3 times, at least 3 times. So we're going to use it, survival analysis. It's not that complicated. The gist of it is this censoring problem. So if I have data that looks like this, so say like I had a bunch of births at time 0, and then at time 10 I take a snapshot of who's still around, or how long did those people live for, or those subjects live for. 3 of them, in the blue lines, they continued on. They existed at time 10. Everyone else died before time 10. So the naive thing to do is just take the mean of all this data. That's going to give you an underestimate because of these blue lines. The other naive thing to do is to ignore those blue lines. That's silly because obviously there's information there. Because in reality, it might look like this. You can't really tell, but it died. This person died like shortly after. So if this is the true data, we have to sort of account for that censorship problem where we only have data from at time 10, up to time 10. So to do that, we're going to do a bit of probability theory, a bit of math. So mathematically, we know that if capital T is this like random kind of lifetime, we can define the survival function as 1 minus its CDF. So we have this case of no censoring. I'll bring it up. We have this case of no censoring where we just sum over all the observed data. However, if we have censoring, say like we can split our population into two. We have the observed and the censored. The observed is the exact same. It's like the log of what we observed as their exact death. For the censored people, though, all we know is that the death happened in the future. We have like t, capital T is greater than 10. I don't know when, but all I know is that it's just greater than 10. So we have this additional term of log s, or the survival function s. You can do the trick of dividing by 1 and multiplying by 1, which is like a fancy way to say like divide by s of t and multiply by s of t, which is still like multiplying by 1. We can do that. We can take some logarithmic properties. This is just here for the derivation if you want to go through it. But at the end, we get these useful functions that are kind of the heart of survival analysis. We have this negative log s of t, which shows up here. We define that as the cumulative hazard, denoted capital H of t. So we stick that cumulative hazard here. And then you can do this a bit more math and figure out that this PDF over S, that's equal to, we denote that small h of t because it's exactly equal to the derivative of the cumulative hazard. Ignoring all that, what you end up with is this much prettier, interesting kind of log likelihood. That's the log of h of t, this hazard function, only at the observed times minus the sum over all the cumulative hazards. So this is what we're actually going to work with. Rather than thinking about PDFs and CDFs and survival functions, there's a reason why we go this route, and it'll be more clear later on. But there's also like a interpretation to what the hazard means. When your hazard spikes, it means you're more likely to perish, or the subject's more likely to perish. The cumulative hazard is just the integral of the hazard. So you can start thinking about hazards. Instead of thinking about like probability distributions, you think about hazards. Like when are subjects susceptible to dying? For a human, there's a high risk early on before year 1, and then it sort of sinks down, kind of rises again during like the teenage years, sinks back down, and then around like 50 it starts to gradually go up. So that's like the hazard profile of humans. We'll see some more examples and it'll become like more interesting or more clear. So now we're going to work in hazard space instead of probability space. Think about hazards from now on. OK, so one thing to take away too is that we're using the log likelihood function to add information about our system. So again, I go back up here. We're adding that there were censored cases. And this is kind of like a common theme throughout today's talk, that we use the log likelihood or the likelihood to add information about our data. It's a very useful idea, and we'll take advantage of it a few times. OK, on to clicking again. OK, so the cumulative hazard for the Weeble is super simple. It's just this t divided by lambda to the power of rho. Much easier than that log PDF we had before. The hazard, if you just do some calculus, is equal to this. It's just the derivative of the cumulative hazard with respect to t. So it's just equal to this. The log hazard, I just take the log of the hazard, of course. And then the log likelihood is just written here the same way as we have it up here. There's this new e parameter, e argument. E is like a vector of Booleans. 1 if that subject was observed to die, and 0 if they were censored. So 0 if they died in the future, and I don't see. OK, so we should get the same thing. We have the same bounds, the same initial argument. It's the same data, but I've added a few censored cases, just randomly. OK, things failed again. That's OK. It's supposed to in this case. OK, first debugging. Oh, I didn't get the. Sometimes you get a negative inf here. Again, that's because we forgot to put this negative sign in. I stress, like, I get so many emails by people saying, like, oh, why isn't this converging? And they forgot the negative sign. So I just want to stress that. OK, so we're going to create a new function called a negative log likelihood, which is a better name than we had before. So if you're following, we're going to put the negative log likelihood into here. Note the args has t and e now because both those parameters are being passed in, and this should just work. Great. OK, so these are our estimates for rho and lambda. And again, I stress it's cool because we actually had partial information about these subjects in the future. We didn't see them die, but we can still do inference on them. If you wanted to, you could like see the influence of those censored cases. Like here, I'm saying everyone is observed. So this is like what 0.43, 0.42. One's like. So yeah, like this parameter, the lambda parameter, changed quite a bit just because we didn't take into account those censored cases. But I want to keep them there. Oops. Great. And we can also like plot the estimated survival function if we wanted. Because of the relationship between the cumulative hazard and the survival function, it's just e to the negative cumulative hazard is the survival function. We can plot the survival function, which is great. And that's typically what the business wants to see. They want to see survival functions. That's also what you're going to use a lot in your business problems. You want to know like what's the probability that the individual survives until time x. So next we're going to move on to my favorite part of this whole track is automatic differentiation. So let's open up part 3. Part 3. So the tagline here, and I love this tagline, is how to differentiate an algorithm. So you might, from second year, first year calculus, or even like third year calculus, know how to differentiate a one-dimensional function or an n-dimensional function. Automatic differentiation is how to differentiate an algorithm. I can't imagine what math notation that might look like to differentiate an algorithm. But you can do it, it blows me away. So you have tools like SymPy, Wolfram, Mathematica that can differentiate symbolically. So x squared differentiated is 2x, and we're comfortable with that. But how do we differentiate something like this? So it's an algorithm. It has this for loop. It has this assignment operator. It's kind of complicated. If you were to write it out in math, it would look like this like very nested sine function. And if you plot it, it's a legit function. It's a numeric function. It might be completely contrived, but like it does give you a numerical output. So how do you differentiate this? Like what's the derivative of this at, say, like 0 or 0.5? You could approximate it using a numerical method by like taking a step forward, taking the difference, and then dividing by that difference. That's like the kind of classical Newton way to approximate a gradient. But that's expensive. As you enter higher dimensions, that becomes infeasible because you're having to do this little like step trick for every single dimension, and that becomes very slow. It's also imprecise, especially around like high, very steep areas. It becomes imprecise. So introducing this tool called AutoGrad. AutoGrad and automatic differentiation has been around for about 20 years, but it's only recently become useful because neural nets are becoming more and more complicated, and that's kind of where its motivation came from, is to like differentiate these complicated neural nets. But we can take advantage of it too for these simpler models, and it totally clears up and cleans up lots and lots of code. It makes your code more testable. It's less error prone. It's really, really nice. So AutoGrad will not compute symbolic derivatives, like 2x versus x squared. It'll compute exact point-wise derivatives. So for example, I have this function rewritten. Importantly, I have to use AutoGrad's NumPy. That's just like a little thing we have to do. It doesn't make a huge difference, but it's the exact same. You just treat NP as the exact same as like np.sign. And we can do something like this. So this negative 0.26 is the derivative of this function at 1. So So back up here, so that is negative 0.26. Wait, sorry, here. Which is crazy. It's like it differentiated this algorithm, which is this written out. And if this isn't complicated enough for you, like let me add in some more things. If y is greater than 0, let's say y is equal to 1 or something, plus x. I don't care. Squared. Like times np dot expy. It does like you can do anything. Let me just make sure this works. Yeah, sure, great, cool. Say again? You can do randomness, sure. It's going to be fine. It's going to return a random derivative, but that's fine.
What's the derivative at 0?
Are you doubting that it's going to do this? 100, obviously. I guess, OK, you can go back up here and put in 0, and I don't know, it would work out, I guess. Oh, because of this. Oh, great. So great question. I love this question. This is such a good question. So what happens at these boundary points? Like a simpler case of non-differentiability is the absolute value. I would say two things. I would say, one, it doesn't matter. And I would say, like, for often, like, you don't need it at 0 or at these differentiable or non-differentiable points. So if you think about a optimization algorithm, the chances of it having to evaluate some gradient at 0 is like close to vanishing out of all like the floating point numbers. It's going to happen eventually, but that's like a minor edge case. It's going to be like a minor noise. You could also like program in what you want it to do at 0 to make it like smoother or something. I mean, we're not working with, what is it, Weierstrass's non-differentiable function or whatever. So this stuff is OK. It's just going to like, it's going to choose the code path that it needs to go down to get a derivative at that point. So yeah, your math professor might have said you can't differentiate absolute value, but you can differentiate algorithms. Yes?
So I have a question. I know this isn't like a calculus course, but can you give some sort of explanation of how autograd works?
Yeah.
It's not doing like it's around.
Totally, yeah. So what it's doing, it's applying the chain rule and the product rule over and over again recursively. So let's take the derivative of sine x squared using autodiff at 0. So importantly, like it's point y, so I'm going to say at 0. So first, it's going to inspect its code, and it's going to start to unpack itself. So it's going to first look at, OK, let's look at the most inner function, which is x squared. What's the derivative of x squared? It has a lookup. So it knows how to differentiate x squared or x to the n. It has a lookup for sine x. So it's going to go, OK, this function is called x squared. The lookup is 2x. So I'm going to put in 2 times my point 0. So then I get 0. And then it goes to the next outer function, which is sine x. It's going to go to lookup. Sine x derivative is negative cos or cos. And then it's going to put in 0 for that.
So if it's doing that, isn't it operating similarly to SymPy or Alpha?
They both have a lookup, I guess, but I think that's where the similarities end. So SymPy is going to return the entire function to you. This is going to compute it on the fly.
Okay.
Yeah, maybe that clears things up. There's like a tree in the background. Yeah. Oh yeah, I think I forgot to multiply by.
So it will take care of it.
Yeah, it'll take care of that. Yeah, I think my derivative was wrong when I said it out loud, but yeah, it takes care of that, all that stuff. So like SymPy would not be able to answer this, but autodiff could. But it takes advantage of these like very, very simple derivative operations like chain rule and product rule and things like that. Other questions? And it's exact too, which is so crazy to me. Like it's not an approximation. This is exact, and you can show it. Like, you can try some things. So f is equal to lambda x. Grad f at 1, it should be 2, right? Yeah, so it's exact. Yeah, which is pretty sweet. Yes, yeah?
How does it know that the input is a scalar and not a vector? Like, how does it know the shape of the gradient that's computed?
That's being inputted?
Yeah.
There's like some Python logic to check if it's a NumPy array or a scalar. Do you want me to try something?
Like, what if you just did like an sign of like of x, and you could give maybe a vector input to sign or a scalar input to sign,
Mm-hmm.
where it be either alchemize or just for that scalar. How does it know? Oh, I see. Like when you're doing the gradient, you're just giving it an example and it refers.
Sure, yeah, but it's also like, because the primitives are still NumPy functions behind the hood, if if my sort of tree, my autograd tree has 2x in it, x can be a scalar or a NumPy array, and it's still gonna, like, NumPy's still gonna compute those things correctly. Just to sort of like make that. Oops. Like this should return. Oh, yeah. So you have to use a different function for that, but we'll get into element-wise. So grad is useful for, or maybe I'll show you one more trick. I'll show one more thing while we're still here. So say I had 2 parameter. No, forget it. I won't do it. We'll get into vector-based things in a second. So you can look it up how this stuff works. If you think about it, like TensorFlow is just a auto diff library. Like PyTorch is just an auto diff library. They're really, really good at it, and they offer like GPU support and a bunch of other tools and like neural network components. But that's kind of what like the core is. You have this very complicated algorithm that who knows how to take the derivative of like a CNN or a like recursive neural net. Autodiff is like, no problem. Like I can do that point wise. You just tell me what to evaluate, and I'll do it. So you can also, just moving on, you can also string together, even though it is point wise, you can sort of string things together and still plot things. Oh yeah, I've modified this quite a bit. Let me just not do this anymore, so it's a bit prettier. So that's the derivative of this sine function that we had before, and it looks like it should. It's the derivative. Okay, so how are we going to use this in our optimization routines? I'm going to pick up the pace list a little bit, sorry. We're going to use this in the optimizer to compute gradients that the optimizer can use, and we can compute Hessians, which I'll get to, which is really important. So same data, same log likelihoods. We can take the gradient of the negative log likelihood just using grad negative log likelihood. Cool. So because the negative log likelihood has 2 parameters, this lambda rho, we return 2 derivatives. It's a gradient. So we have 2 outputs, one for the gradient of lambda, one for the gradient of rho. This is evaluated at 1, 1. And we stick it in using this Jacobian, also called the Jacobian argument. So Jack equals this. And we print the results, and we get the same thing. It's different data, so we get slightly different answers, but yeah. We can also actually make this a bit more efficient. We can use this value and grad, which returns the value of the function and the gradient of that function in one call. So how this works is we set Jack to equal true, as you can see here, and we put in just negative log likelihood here. This value and grad was kind of designed for minimize. So this just makes things more efficient, because I can compute, if you think about the gradient calculation and the actual function calculation, they share a lot of shared symbols. Like there's a sin x in some places and a sin x in other places. This just computes the entire tree, and it just makes both the gradient and the actual function calculation faster. And we get the same results. Great, cool. Moving on to part 4. Oops, well, that's not what I want to do. Okay, so let's start thinking about generalizing our model. So previously we had this Weibull distribution. Why did we choose Weibull? Who knows, just because. So we're going to shift our data a little bit to the right, just kind of like add a little constant to shift it to the right. let's create this new parameter called mu, which is actually like, it tries to model our shifted data now. If you think about the log hazard, okay, so what was the hazard? The hazard was the derivative of the cumulative hazard. But a derivative, like, let's not compute that anymore. Like, why are we computing derivatives by hand? Let's use autograd. So we're going to do, the log hazard is just the log. Did I do this later on? Yeah, I did. OK. So the log hazard has this, could be complicated. I don't really know what it is. We have this new mu thing. It could be mu squared. It could be whatever. But we're going to use autograd to do that computation exactly for us. So note that the derivative is respect to t with the hazard. So that's the argnum equal 1, or like the second position. So we put in 1 here. So we're saying take the derivative with respect to the second parameter t. So this is our hazard. The log hazard just becomes np log of the hazard. Oops. So we get the gradient with respect to the 3 parameters in the log hazard. So in summary, like, don't do derivatives anymore. Don't calculate derivatives by hand unless you need like performance or speed and you're not going to make a mistake. Just rely on or lean hard on autograd to do the derivatives for you. So this is the same code as previously. Negative log likelihood, we throw it into our optimizer. And notice too, we have this new parameter mu. So I give it the initial starting point of 0 because mu could kind of be anywhere. It's like a shift. It's like a location parameter. I also have to be careful though with adding it to my bounds. So I have this kind of like bounds logic. Print the results, and we kind of get what we expected. When we added 4 to our data, we've now subtracted 4 in this mu parameter. So everything kind of worked out great. And if you're good at like now parameter counting, the idea of like how many parameters does the model require, how do I deal with like arbitrary x naught and arbitrary bounds, you can kind of just create whatever parameters you want, or whatever parametric models you want. Like I could go back up here and add in more parameters if I wanted, because maybe my data has slight subtleties that I want to model. I want to add in a few more like hazard functions, and I can combine it all and get this new function. And if I just change a few things here, everything just works. This also can be extended to regression models. So I have, say, lambda x. This is with no more location mu stuff. I have this lambda x, and say lambda x is a function of 2 covariates that maybe are relevant to my problem. So I'm just creating some regression data here. This all is like the exact same code as above. I just have this additional x thing. And then in my cumulative hazard, I just have to like kind of do a numpy dot product. That's about it. Create this new lambda, and then this is identical to what we had above. So I have how many parameters or how many unknowns? I have a row. I have beta 1, beta 2. So I just need 3 initial arguments, some bounds. My betas can be both negative infinity to positive infinity. So I have nuns here, but this should. Oh yeah. So we have to fill this in. What should go here? So params, if you think about it, so lambda, log lambda coefs. That's just the first 2 params. And then the row is the last one, like that. So I'm kind of just doing an unpacking. And we get the results back. So this can be extended very easily to regression models. So you might be asking, like as a good statistician or data scientist would, like what about my variances? We've only been doing point estimates. I want to talk about like variances. I want to know how uncertain I am. And that's great. That's like the kind of Bayesian attitude I like to hear. So we're going to move on to part 5 and discuss that. So under some conditions that I won't get into for brevity's sake, but you can look them up. What's cool is if you think about your MLE problem, your maximum likelihood problem, which is what we're doing. There's maybe this bowl that you're trying to minimize and find the bottom. What's cool is the second derivative at that point, at that minimum, that's called the Hessian, and that tells you information about the variance of your parameters, your unknown parameters. At least like once you take the inverse of that and the diagonal. So you have this H, which is the Hessian evaluated, the second derivative, evaluated at the minimum point of your bowl. You take the inverse of that matrix and take the diagonals, and those are the variances of your parameters that you just fit. And you might be thinking, okay, wait, why do I have variances on my parameters? Well, you just did like a statistical problem. There should be variances somewhere. If I had like 2 data points, there's going to be a high variance in those parameters. So we want to be able to reflect that. We want to be able to say, like, yeah, there's still uncertainty in this system. And this is how you can do that. You just take the Hessian, and then you invert it and take the diagonal. But again, like the second derivative, let's not do this by hand. Let's use autograd. So there's this function called Hessian. Well, first we generate some data, and we do the fit, and the fit's fine. Did I forget something? Yep, okay, great. Fit's fine. I think this is the same model. Yeah, it's just a Weibull model. So the fit's as we expected, great. So here we're going to do the Hessian, this Hessian function of the negative log likelihood evaluated at that minimum. So there's that bowl, here's the minimum. We want the second derivative at that minimum. It's a matrix. It's like the second derivative with respect to all arguments. So it's a matrix. It's a 2x2 system, so we should have so it's a 2-parameter system, we should have a 2x2 matrix, which we do. Great. So using that equation above, we just take the inverse, and this is a bit too small, sorry folks. We take the inverse and then the diagonal, and we get variances on these estimates. So that was like really, really easy and cheap to get variance parameters on this model. Taking the square root gives us the standard deviation or the standard error. And finally, we have this beautiful, very, very easily done kind of summary table. So we have our estimates plus our uncertainty on those estimates. To prove it, like you can go back up and change the sample sizes. So let's make that 100, and we should see a like increase in the variances as expected. So that's again just leaning on some principles of maximum likelihood estimation, that the Hessian contains variance information, and then again leaning hard on autograd to do that Hessian calculation for us. I remember I was trying to do this. This is pre-autograd. I was trying to calculate the Hessian for the log normal model, for a survival model, and it sucked. It was like awful. It took me forever to do, and it was this big, long, I put it in Wolfram Alpha, and it was this huge, massive, long thing. Like each element of that matrix was this big, massive, long thing, and it was error prone as I was typing it in. It was such a hassle, and that was like the simple log normal model, which has like again 2 parameters. This just did it no problem. Like I could change my log normal model to anything more complicated, and this is just going to do it the exact same way. So this was quick, but I want to show you the next part, which I think is really important. We also want to talk about the business, right? You're not going to go to your CFO or your PM or your fellow researcher and say, like, yeah, rho was less than 0.5. They're going to be like, wait, what? What's rho mean? Often there's a business reason for doing this, and there's a business function that connects your parametric model to some outcome. So we'll do that next in part 6. Yeah, so I mean, here's a story. You know, the CFO wants to know what's the variation in churn, and you tell them lambda's been increasing, but rho is staying the same. And then the CFO says, you know, what banana value is increasing? What are you talking about? So what we want is a connection to our business problem. Keep in mind, we've only been working with the cumulative hazard. We haven't really talked about the survival function in a while. But let's say we want to actually present the survival function to our CFO, or our stakeholder, or the medical professional. So we want to know what's the confidence interval, the CI, for the survival function at these best values, at like the maximum likelihood estimates. Okay, so there's this great thing called the delta method. Think of it as, if this is more appropriate, I'm linearizing the problem to create like a simpler model. But essentially, the variance of some f is like your business problem. In our case, f is equal to s, the survival function. It's equal to the gradient of f at the parameters times the variance matrix that we just calculated, times the gradient again. So we know what the variance of the parameters is. That's the inverse of the Hessian. Do we need to compute the gradient of f by hand? No. Let's, again, use AutoGrad. F could be something very, very complicated, which we'll see in the next part. But for now, f is just going to be the survival function. So going through, we've seen all this. This is the same old, same Weibull model, two-parameter Weibull model. We execute. Great. So we have this new function called the survival function. And this takes in parameters, takes in a time. And we know the relationship between the survival function and the cum hazard is just negative, exp negative. OK, so this next part, so what's the variance at t? If we use, gradient of s of f. This is just gradient of the survival function, as we've kind of seen, again, gotten used to. Cool, so that should work if we execute. Yep, so we have the gradient of the survival function at these parameters, these optimized parameters. So the variance at t is that matrix multiplication above. So it was grad of f, or survival function. Sorry, I already have this, grad of sf times the estimates at t, dot product, or what is it? Dot product, the variance matrix, which I did not run, I don't think. Oops. Variance matrix at, or multiplied by the gradient of SF again. At t. And is there? Yeah, that's it. So if you think about it, this is 2 by 2. This is like 2 by 1, as we saw. This is 1 by 2, or 2 by 1. And so we should get a scalar at the end. And we do. Cool. So this is the variance of the survival function at time 5. And from that variance, we can construct standard errors and then confidence intervals, which we'll do next. Cool. So this function was just this equation up here. And again, I don't have to compute the gradient of survival function. AutoGrad did that for me. Yep.
At the bottom of the main block, when you compute the variance, don't you have to take the diagonal of that?
No. So the diagonals for the variance of the point estimates.
Oh.
What I need is the, yeah, it's not so clear. This is a matrix of it's the covariance matrix. Yeah, yeah. Yeah, so that's the covariance matrix. But yeah, so that's how to get the variance of a function, a business function. The next, if we move on to part 7, this will be a much more applicable example, I believe. OK, so let's look at like a lifetime value example. If you're not familiar with SaaS businesses, like subscription businesses, they have this very predictable churn cycle. So it's because SaaS businesses work by, we charge them monthly, or the company charges them monthly. At the end of the month, at the end of like a 30-day cycle, there's a big drop off in customers. And then it's pretty flat. There's some churn, but then big drop off at day 60 and so on. So very predictable. But you might not know, what's the rate of churn in those kind of predictable intervals. One way to model this is like a piecewise hazard. So you might have low churn initially before tau 0, and then between tau 0 and tau 1, there's a high churn, and then back down to low churn, high churn. So it's this piecewise model of hazard. So that's kind of how like a SaaS business might model its churn. So there should be, if this doesn't work, let me know, but there should be a churn data set in that repo that we can just copy. I think I have not yet. You can plot it if you want. And I don't think there's any censorship, but it doesn't matter oh no, there is censorship, yeah. So the breakpoints, that's for us to decide. I'm going to decide that it's on day 28 when the regime changes, when the customer kind of mentality changes and they're about to be charged, they might churn. So on day 28, between day 28 and day 33, that's that spike. And then between day 33 and day 58, it's kind of low again, and then spike, low again, and so on. So it's up to us to define this cumulative hazard function. Again, it has the same signature, params and times. In this case, though, this is like some serious NumPy black magic in order to get this. We can chat after, but just assume this is going to give you the cumulative hazard of the piecewise constant model. Stop reading it, everyone. It's going to hurt. So again, we have hazard is just the element-wise grad of the cumulative hazard. Cool. It's cool. I just want to point this out. Like I write this once, and then everything just works. Like I don't care what the hazard is. I don't care about log hazard or log likelihood. It just works. Okay, so we get the optimization. I think we had, I don't know, what, 9 parameters that we estimated. That was pretty fast. So these are the lambdas, the hazard rates in each of these these time periods. And we can plot that. And this is, so this is what like a survival curve of a SaaS company might look like. I see some nodding heads, like, oh yeah, this is familiar. But that's what's happening. These kind of big jumps are like when we're about to charge them, and the customer's like, oh no, like I'm bouncing from your service. And it kind of flattens out because you sort of lose the weak customers in this kind of churn period, and you get like better and better customers over time. That's kind of what it looks like. But let's say like this is our business problem. Let's say we on day 30 we charged users $10. That's like the first monthly cost. And then on every 30 days after that, we charge 20. It can be more complicated, but we want to know what's the LTV of a customer, and what are the CIs, the confidence intervals of that customer. That's like a non-obvious problem, I think. If it's not obvious, you can make this complicated, or this function more complicated. So I think I have time. Yeah, okay. So let's do. We're going to do it this way. LTV is 0. Again, we're going to differentiate this, which is kind of crazy, but just write it like you would normally write a NumPy function. So LTV equals 0. This is going to work. LTV plus equals, it's $10 for the first month times the survival function, which, how did I write that? I have to look. Oh, cool. Okay, so it's $10 times the probability of surviving at time 30. So it's survival function, which is defined up here, just the negative cumulative hazard, times, or at time params, time 30 days. And then for, like day in range, list. Let's do 60, 90, 120. LTV plus equals $20, right? Yep. Times survival params day. So you might have a discount coupon code or something that you want to include in this business logic, or you might want to include cohort details in here or something. Kind of whatever you want. This is going to connect your mathematical parametric model to what the CFO or the PM wants to see on their desk. And I think this is going to work. Ellipse. Oh, yeah. Who knew that, eh? Did you guys know that? That's so interesting. I didn't know that. I think I did know this was an actual Python thing, but I didn't know it would print out like that. Okay, LTV. That's great. So in this case, the best estimate of the LTV, because we already fit the model, the best estimate of the LTV at 120 days is 51. Cool, $51. But more importantly is the CI. Like if we have a massive variance in that LTV, we might want to change our strategy, or even more appropriately represent in some viz that uncertainty. Okay, so the variance of the LTV, or the variance of the LTV, that's going to be equal to the grad of LTV 120 evaluated at estimates params. I think, or am I way off? I think I'm off, actually. Yeah, I'm way off. Sorry. The variance involves that complicated matrix stuff. So it's the delta method again. So it's the grad of the LTV or the business function times the covariance matrix times the function again, the grad of the function again. If I'm typing too fast and you're not keeping up, I'm sorry. Just let me know. Cool. So what do we get? 1.6. And take the square root. That's the standard error. And we can compute the confidence intervals by just looking at, like, say, the 95th approximation or whatever this is. I forget. But this is our confidence interval for the 120-day LTV model. Just trying one more thing. Let's go back up here. Let's just truncate the data by a lot. Let's just remove up to 100 points. And was that an error? Oh, there's too many parameters and not enough data. Yeah. Let's do 200. Great. So yeah, we have a wider CI as expected. So when's this talk? It's till 2:45, right? Okay. Okay. I will let you all look at this on your own time. It's interesting. It adds a bit of a Bayesian pooling model to this model. I'll quickly jump in. I'll quickly explain it. I'll just say, let's say I assume, and this is probably correct, that the in-between periods, the rate of the in-between periods, are correlated. In the above model, we just let them be whatever they want it to be, the best, like just curve fit. But let's assume that we think that the churn rate in the in-between periods is correlated. Also, the churn rate in the high churn periods is correlated as well. So we can add some additional information to our model. And so you can run through this and kind of explore what happens if I do that. So again, the story behind this is we use our likelihood to add more information, some prior information about our system. And we can do we get better statistical efficiency by doing that. Okay, but yeah, you can all look at that. Okay, so we move on to part 8. And this is a quick one. It's just the idea of optimizing over an unbounded space, which is typically more efficient and more robust. Your estimation's more robust. So in all of our previous models, we had the boundary condition of parameter must be positive. So we had that 0, none in all of our optimizations. I mentioned this because this is another problem that I see a lot of people run into. Instead of optimizing and having that bound, we can take the log of that parameter, which turns it into a number that can be from -infinity to infinity. And we optimize over the log of the parameter. I'll show an example in a second, but the same thing applies to if we have a parameter that sort of fits between 0 and 1. We can express it in real space, in between -inf and inf, and then take the xbit function, which converts it back to be between 0 and 1. So the important thing is that there's a 1-to-1 correspondence between values in the real line and 0 and 1 through this function. So for example, we have this churn problem again, and instead of instead of putting the params and assuming the params are going to be positive, let's assume it's the log of the params. So we take the log of lambda, which is going to be which could be any number, and then inside our model we just exponentiate them to make sure it's still positive and we still have like meaningful cumulative hazards. And so if we do that, oh, what goes where? Oh yeah, here. So notice too we have this, again, no more bounds because we're not assuming that the parameters are positive anymore. We're just saying like pick anything. Our model's going to kind of like convert it back to positive. And then here, if we want to recover the original parameters, we just do xp of the log of the estimates. Cool. And if you go back to the previous part, you'll see that that's the exact same thing. So this is just a way to get around complicated bounds. You just model it as a real number and then use some converting function, a one-to-one function, to go back into the space that you actually want. It's just more efficient to do it that way. You can take advantage of more complicated algorithms, optimization algorithms. So the funny thing is, like, this is exactly what Lifelines does. Like this entire tutorial up till now, that's what Lifelines is really doing under the hood. It's just using AutoGrad a lot to do all these calculations. It has classes, whereas we've been using functions. And Lifelines is, like I said, good at parameter accounting. The idea of like, okay, how many parameters does this model have? That's how I have to like specify my optimization signature. Great, so that was the extent of the computer tutorial. We're going to move on to the interpretation, the modern trends in inference. I guess in summary of what we just learned, like AutoGrad is crazy and awesome, and use it to your advantage. Computing derivatives by hand is old school. It'll be like, like sorting was in 1940. Like, you learned it and you had to do it by hand, but then algorithms came along and just made it way better. 1940 is the wrong year, but you get the idea. Where am I? Okay, so we did that. So now let's talk about interpreting what we just did. We talked a lot about, like, we saw some CIs. We didn't see p-values, but p-values is just the point estimate divided by the variance. We didn't look at that, but that's also very common in especially like software output of models. You'll see a p-value. You'll see CIs. Let's talk about what those things mean and when they're not good and when there are better alternatives. Okay, so like I said, you might get output after running one of these models. I'm actually going to switch. This will be easier. Just going to change my arrangement so I can see what you see. Excellent. Okay. So talking about the p-value first. The p-value has something to do with a null hypothesis. I don't want to get into like what the p-value really means. The most important thing is that it's often misused. There are cases, and I'll preface this before I get into more, there are cases where p-values make a lot of sense and you want to be using p-values. I'm thinking like reliability engineering, where you have the same experiment constantly. You're constantly pulling things off the line and checking things. That's where you do have this kind of frequentist paradigm working really, really well. But if you're doing a one-off experiment in psychology or in the lab, p-values make less sense and they're often misused, as we've seen with the sort of crisis going on now. So that's something to do with the null hypothesis. But what is the null hypothesis anyways? Gelman argues, Andrew Gelman, who's a famous Bayesian at Columbia, he argues that the null hypothesis is never true, which I really like. The null hypothesis is, say, like beta equals 0. But like you really don't think ever that beta is exactly 0, right? Like that just doesn't make any sense. It's almost, it's completely unlikely for beta to equal exactly 0. So he argues the null hypothesis is always false. It's kind of a tongue-in-cheek thing, but it's kind of true. It's like the fundamental part of null hypothesis testing is kind of on shaky ground already. One thing to keep in mind too, when you get these outputs from your software, is that tiny p-values, like 0.0001, whatever, when you have lots and lots of data, they're probably due to a violation in the assumptions and not any real effects. So recall what the assumptions are in any kind of statistical model that uses p-values. It's the assumptions, the null model you're really testing is the assumptions plus h naught. So assumptions in this case is like, do you have a linear model? Do you need that interaction term, or do you not need that interaction term? These kind of assumptions that you're making with your model. So a tiny p-value might mean, oh, you just violated a linearity assumption. And your p-value is very, very small, not because you got rid of the null hypothesis, but because you just violated something. It's more obvious with big data because the model's better able to see that assumption being violated. So there's things you should worry about instead of p-values, like a poorly conceived research question or poor data stewardship. Each one of these, I've experienced and I know is a problem. Sloppy research procedures, poor measurement, that happens all the time. Avoidable errors in the analysis, just the wrong model altogether. The sources here, but yeah, the same thing. These are all probably bigger problems in your research or your analysis than a small or large p-value. A newer thing, so assuming that you're happy with p-values, or so you're not happy with p-values, but you've kind of checked off all the potential problems. A new thing that is coming around is called s-values, and it's the base 2 log, the negative base 2 log of the p-value. So why is this preferable? Well, at first, it's not used as a decision criteria. We don't say oh, the s-value is less than -7, therefore we accept the alternative hypothesis. It's not. It's more a measure of surprise or information. It's base 2 for a reason. Base 2 can be used to think about information and entropy. Logs are also the right scale to think about probabilities. So the p-value is a probability. The raw probabilities are really hard for humans to interpret. And a good example of this is, say, p is equal to 0.5, and I want to add 0.01, a very small increment to 0.5. It might only take me 2 tosses to it might take me thousands of tosses for me to notice that difference, that I biased my coin a little bit. Instead, if I added 0.01 to 0.98, it might take me 3 tosses in order to detect a difference. That analogy kind of sucked, I'm sorry. The important thing is that raw probabilities are not linear like money is or like lengths are. Probabilities are sort of stuck between 0 and 1, and that completely distorts how we look at them. The log is the right way to look at probabilities. So this kind of linearizes the probability, and we can speak more meaningfully about a -7 versus a -5 s value, whereas a 0.004 p-value, how do you compare that to 0.002? Because it's not a difference of 0.002 in the same way. And finally, the analogy to think about as well is a p-value of 0.05 is 4.3 bits of information. It's using a coin flipping analogy that's barely more surprise or information than just seeing about 4 heads comes up in a coin flip. 4 heads coming up in a coin flip isn't that impressive, but that's kind of what a p-value of 0.05, which is the gold standard and what everyone uses, is saying. So this is again a perception issue. The log is the right way to think about probabilities. And then there's also the trend of removing asterisks from p-value tables. You see a table, that's very small, I'm sorry. You see a table like this with these asterisks beside the p-values, or beside the estimate to say this is how significant it is. That's inappropriate technically if you're using a null hypothesis testing framework. The problem is that p-value significance is a binary thing. you can't say this is more significant than something else. So whether it's 0.001 or 0.005, they're both significant. It's also moving the goalposts after the fact. So what you're saying by putting these asterisks in, you're saying like, even if we had chosen 0.0001 as our sort of threshold, as our alpha value, we still would have confirmed this hypothesis. So you're kind of like moving the goalposts after the experiment's been done. So using asterisks in papers is not really the right thing. Type 1 and type 2 errors, these are always confusing to me, and I don't think they're the right way to think about these problems. Gelman, I mentioned him, he introduces the idea of two new types of errors. The first is type S, and this is what's the probability that you got the sign wrong in your estimate? And that's really useful. Like, you don't want to get the sign wrong, but you want some way to measure how wrong you might be. If you get the sign wrong, you might be giving a drug that is harmful to the patient. You might be choosing a path for your business that has negative consequences. So that's type S, the probability of the sign being wrong. And then type M is the magnitude, which is also very important. How off are you in the magnitude of your point estimate? So these are much more interesting conceptual tools to think about your parameter, rather than like type 1, type 2. These are like concrete kind of things that we can communicate and understand better. Confidence intervals have a very complicated interpretation, which again, I don't want to get into. The newer way to look at confidence intervals is, or here's a story, I guess. So some researchers who were looking at the negative effects or side effects of a new anti-inflammatory drug, they noted that the risk ratio confidence intervals were 0.97 to 1.48. Technically, because 1 is inside that confidence interval, the null hypothesis can't be rejected. So they concluded that no harm reduction, or no harm would come by using this drug. But that's very silly. It's like 1 is barely in that interval. If just by chance the risk ratio is actually 1.48, you're causing harm to patients. And kind of likely it is going to be greater than 1 if I look at it this way. Yeah, the p-value in this case was 0.091, so they didn't reject the null. But it's strange for them to not do something about that. This is kind of alarming. But if you're blindly following this kind of p-value decision criteria, decision thresholding, you might miss this. So what you want to do instead is look at the most extreme left-hand side and the right-hand side of the interval, and then interpret what would happen in those extremes. So in that anti-inflammatory drug case, they would say either there's no harm reduction, like it's 0.97 is pretty close to 1, or they would say like, oh, there's actually a valid concern that we were actually harming patients by giving them this drug. And that might spur more research or more funding into looking at this drug, rather than just saying like, oh, it's fine, let it go. So you want to look at the point estimate limits. And technically, all values in that interval, that confidence interval, are valid. You can't say this is more likely than this one, technically. But that's a very useful interpretation. Someone yesterday in one of the talks, I forget which talk now, but they said using the lower bound and the upper bound as like the extreme cases for your business. And I kind of like that, like the best case scenario, worst case scenario. I think that's a good way to think of it too. So there's the old school thoughts around like the testing framework of science, where we have null hypothesis tests, and we want to use like p-values and alpha significance levels to sort of decide what's true, what's not true. That has the accept, reject hypotheses, the p-values as its decision criteria, type 1 and type 2 errors. Instead, we want to move to this estimation framework, where we're looking at estimates and CIs and interpreting them. We're not blindly following this rule. We're saying, okay, what's actually happening? Like, what can I meaningfully interpret in this situation? Sort of abandoning null hypothesis testing because there's too many problems with that, with p-value hacking and whatnot. And then thinking about like type S, type M errors. These are much easier in the Bayesian framework than in frequentist framework. So thinking again about my priority list, try a Bayesian approach, first for your situation. If that doesn't work, try frequentist. And if you want to follow people on Twitter who I think are great and are talking a lot about this and sort of proposing new ideas, I like these folks. They all have like something interesting to say. This Prof. Matt Fox, he has a great podcast with some of his friends called, oh no, it's what is it called? Association something. Oh, what is it? Forget it. I'll post it later, or it'll come to me. But it's a great blog post where they discuss a lot of these problems as well. So yeah, follow these people. You'll learn a lot from them. Real associations? I'm blanking. Questions, comments? Thanks again for attending my tutorial. I hope you learned something. And yeah, take it back to your coworkers and lab mates. Thank you.
I was curious about a couple of things that seem sort of out of place if you were going to maybe argue for Bayesian approaches. And I'm not saying that was wrong based on what you said, but it occurs to me that if you already are going to do Bayesian things, what's stopping you from just moving to credible intervals instead of confidence intervals? And if you're going to talk about the consequences of something that your tails, then why not just go to a posterior risk approach with the cost of the decisions?
If you can go Bayesian, like I said, like go that way to interpret things, with probabilities, and it's really nice. I think unfortunately a lot of people can't go Bayesian for technology reasons, for like education reasons, or the problem's just too complex or something. So I would say like nothing's stopping that. I guess I'm offering an approach to the case where you can't do Bayesians. But if you are doing Bayesians, you're absolutely right. Like the posterior risk distribution is the right way to do things. Credible intervals are awesome and like easy to interpret. So I would say like you're right, but if you can't do that, do these. Yeah. And unfortunately, not unfortunately, I shouldn't start wars, but like people still do frequentist stuff, and that's fine. The majority of people still do this. Other questions? Yeah.
So I think the idea of an S value is really interesting. Can you interpret S values? Right, so it's a negative log-based p-value?
Yep.
Okay, so thinking about, all right, p-value of 1, that's going to be 0, right? That is your level of surprise in that p-value, which makes sense at 0, right? So no surprise.
Yep.
What is that doing as we're moving towards 0 with the p-value? And can you discuss the implication of that?
Sure. To repeat the question, so can you interpret the S value more? For example, the S value, if the p-value is 1, the S value is 0, which makes sense. And then as p-value gets closer to 0, how does the S value change, and what is the interpretation? You can interpret it as like the coin flip analogy. I think is correct. So as the p-value goes to 0, you have more and more coins that are landing heads, and you should be more surprised. If you flipped 15 coins, they're all heads, something's going on there. But if you flip like 4 coins and they're all heads, it's like, well, that's just could happen by chance, not so important. Some p-values, like some experiments are so well designed and there's such a large effect size that the p-value is on the order of like 10 to the minus 6 or 7 or 8 or something higher than that. I think people's brain kind of loses understanding after a few exponents. But in the S value case, it's like a linear system. So you're going to see an S value of like 200. And that's easier to interpret than a p-value of 10 to the minus 9 or 10 to the minus 10 or something. So there's that value too. You can also, like, there's an additive argument, like S values can add together, whereas you can't add p-values together. So there's that piece too. Yeah, but I think the information or surprise approach is the right approach. Yeah. Any other questions about? Yep.
Do you have any experience or opinions on using the TensorFlow gradient tape API for computing gradients and covariance and all that for functions versus autograd, like pros and cons
Yeah, I don't have any opinion on TensorFlow because I've never directly used their autodiff functions. So I mentioned AutoGrad. The maintainers of AutoGrad have moved on to Google, actually. They got hired by Google, and they're now working on this new package called JAX, J-A-X, which is really cool. It's supposed to be kind of the replacement for TensorFlow one day. Probably not because there's so much momentum behind TensorFlow, but it's again just an autodiff library, but it has like neural network components to it, and you don't have to use the TensorFlow API, like the kind of complicated data structures that they provide. With JAX, you can use just NumPy functions, just like AutoGrad. Like technically, JAX is a drop-in replacement for AutoGrad. I think it's overkill for what I need, and it also doesn't work well on Windows yet, so I'm sticking with AutoGrad for most of my purposes, and it's faster too, and a bit easier to debug. So that's my answer, that I wouldn't use TensorFlow for autodiff, I would use JAX for autodiff. Yeah, given the choice. And I implemented like a really simple neural network library using JAX, and it was like so simple to do with JAX. And so JAX is cool too because it offers GPU support natively, just like TensorFlow does, but JAX code just reads a lot easier. So yeah, I like JAX. Any other questions?
Yeah, thanks so much. This was really great. And maybe do you have time for that bonus content or part 7?
Sure, yeah. I'll take a question though if anything is available. No? Cool. Okay, so quickly, where were we? We were talking about, oh yeah, so I added this weird thing to my likelihood, because I want to add information to my likelihood, that the variance of every other parameter, because remember my parameters, one describes in between, then the churn, in between churn. So the variance of every other parameter, I want it to be very, very small. And that's kind of described here. I have this, it's a penalizer term if you're familiar with like penalizers and regression. It's a penalizer term on the variance. I want my variance to be small for both the in-between periods and the churn periods. So this, like, I don't know how to differentiate this. I've never seen a penalizer with this kind of weird variance term in it. Usually you see like the absolute, or the L2 norm of parameters is small. I'm doing something with like variances that is a function of the mean, which is like a function of the parameters. It's kind of complicated, but this just chews through it. Like let's just execute this. And it converges fine. And we can see the hazards. Note that there's no variance between the heights of these. As I should make one point, I put a very high penalizer on here. I'll change it in a second. I just wanted to show it as a proof of concept. So there's no variances in these heights. There's no variances in these. If I quickly just change it to the survival function, we can see what it looks like in the survival space. I'll go back up here and I'll sort of tone this down to, say, 10 to the 8. And we'll go back to the hazard. It's easier to see. OK, there's still no variance. It's still too high. Let's try 6. So we start to see like a bit more variance because I have less of a penalizer on the variance in the different terms. The Bayesian interpretation of this is pooling. If you're familiar with like how pooling works in the Bayesian world, I have like, how do I say this? I have like the in-between parameters and the churn parameters coming from a family of or one distribution kind of, and I'm penalizing the variance on that family. So this is analogous to Bayesian pooling in an MLE framework. It's just nuts, in my opinion, that you can just add these terms, differentiate it. Like I could put in, again, I can put in anything I want, squared, sure. Whatever the hell that means. Or the square root, that makes more sense. The standard deviation, yeah. I didn't like that so much, but you get the idea. So you can do wild things like that. That's the idea. Again, the other kind of thing I want to emphasize is like I'm adding information about the model, about my prior knowledge about the model and the data collection into my likelihood. That's like the source of inference. Cool. Any questions? Sure, real quick.
Briefly, just, I guess you told us a little bit like the kind of assumption you made in the choice of the model that we use to apply for one side. I guess
some of it comes from just prior knowledge. Like if you know there's going to be domain knowledge, that's right. Some of it can also be done using the AIC or I guess AIC in this case, the information criteria. You can use that to compare different models together. That just relies on the likelihood and the number of parameters, which are, I mean, in this case it's, hold on. In this case, this is the likelihood value. So you can do things like that, yeah. Okay, that's all for me. I'll be around kind of the rest of the day. We can chat more if you want. Yeah, feel free to share this, and thanks again for coming. I really appreciate it.